Hi everyone. In this chapter we will be studying relations and functions. In this lesson we will be looking at how to interpret graphs.
Okay, so now we're going to take a look at graphs, okay, at the specific representation of functions and relations that a lot of us are familiar with and you've looked at for a few years actually up to this point. Now we're going to kind of do a little bit more of a formal look at it. So bear in mind that we get information every day, and a lot of times especially when you're on watching TV or you're on the internet or even billboards, whatever, you're going to see a lot of times information is presented in the form of a graph, just because it makes for easier conveyance of information. When it's in a visual form, it's so much easier to interpret. So what a graph is here is just a two-dimensional picture. It's a representation of how two quantities are related. Okay, specifically, we've got here the independent variable, and we've talked about this at length already. The independent variable is along the horizontal axis, and the dependent variable goes along the vertical axis. Okay, so in this particular example, what we're looking at here is the way money depends on the number of cars that are washed. And so you can see right now that this is going to be discrete data. Okay, and that's because this doesn't come in intervals. Okay, it's not like I suppose you could argue that we're washing a car and then we ride along here until it's done, and then we ride along here until it's done, ride along here until it's done, sort of thing. So we're partway through the one car or whatever. But you could still interpret this as just discrete data, like you don't get paid until that car is washed, so you get these little dots here. But you could make an argument that this maybe perhaps could be written out as a discontinuous graph. But anyway, the point being here, though, that we can represent these things visually, okay, with the independent variable along the horizontal axis, the dependent variable along the y-axis there. Okay, so now we're just going to take a look at some examples and get used to interpreting what's going on here. Actually, maybe I should just talk about this real quickly here. Notice that what we're seeing here is this nice, beautiful little trend in the data. Okay, every time we go up by one car here, the increase in price goes up by the same amount. It's just this nice, steady growth here. Okay, that's what we're trying to yank out of this graph here. A couple other things you notice that it starts right at 0. You don't make anything when you don't wash anything. Okay, and it goes up at this steady rate here. There's a lot more things that can be said about the graph, but we're going to see those and explore those as we go through the next few examples. So one of the things that we want you to be able to do when you look at a graph here is interpret it, okay? So like it says here, it says when we see graphs like this, we can describe a situation that the graph could possibly represent. And there are numerous situations that could be described. So here's the information here. What we want to do is we're going to just zoom in on this a little bit here. Just take a look at what's going on here and see what it says here. So notice for this little bit right here, okay, this little bit right here, this is a very steep increase, okay, in the value. Now, so what that means is we jump up here from a value of 5 to a value of 11 just with one move over in terms of the horizontal variable, in terms of the time here. So this is like the distance time graph here. So this is a very, very quick motion here. I went from 5 meters to 11 meters in 1 minute. Okay, so it's not very fast, but anyway, but you get the idea. This is quite steep. This is a steep increase. And then here we drop from 11 down to 7 here, and it takes here just these 2 minutes here. And again, that's a relatively steep drop. Okay, so the distance increases quite quickly. It drops relatively quickly, but not quite as quickly here. And then notice what's going on here. This is a constant. Okay, in between these two times, between 3 minutes and 5 minutes here, there's been no change to the graph. It stays constant. Then we've got this, what we might call a moderate increase. Okay, it's not a very steep line. Okay, it goes up 1 meter for going over 1 minute. But here we've got this dramatic decrease, okay? And then here's a fairly moderate decrease. So there are a couple of things that you need to consider here. First of all, in order to interpret the graph here, number one here, is it increasing? Okay, is it increasing or decreasing? Okay, in other words, as you read the graph left to right, and we always read these things left to right here, is the graph going up or is it coming down as you read it left to right? That's an important thing to understand here, because I mean that's a trend in the data. We need to be able to identify that. The second thing is, how steep is it? Okay, so the steeper it is, the larger the change that's going on here. Okay, the more dramatic the change here. So with a distance time graph, basically the farther you go in the shorter amount of time, that really just means you're going faster, right? So in this particular example here, this has to do with speed. Okay, and then we get this other scenario here, just 3. Now it's kind of related to this, but I want you to understand that that a horizontal segment is kind of this part way in between here. It's part way in between. It's not increasing, it's not decreasing. Okay, it's just holding constant here. This is a constant value, and I want you just to understand what that means when you see it as well. So whatever variables that we're comparing here, when you see a horizontal portion of it, there is no change in the graph over that little section. Okay, now here's another graph. And one of the things we want you to be able to do is look at a scenario like this, or a graph like this, and think of a scenario that might correspond to this. What might the independent and dependent variables be that would give you a graph like this? Okay. Now, this might not seem like an overly mathematical sort of a question. I mean, kind of use your creativity, come at it however you want here. But actually, that's highly mathematical, because can you pull meaning out of this? A big portion of mathematics is being able to not just do the math, but to be able to pull meaning out of that mathematics. Do you understand the kind of relationship between the independent and dependent variables that might be implied by this? And here are some examples. Okay, the height of a person on the ground while above the ground while riding a Ferris wheel. Now you might think off the top of your head that, well, that would be something like this, going around and around like that. But actually, if you let time be on the horizontal axis, then you can't do that. You can't allow it to come back like that, because then it would look like you're traveling backwards in time. So what happens here is you start low, you go up, and then you come back down again, and you go up, and that's why time is on the independent axis, and height would be on the dependent axis. You could think of this as the time of the sunrise throughout the years, right? Because let's face it, there are when you're in summer, you got a very early sunrise, but when you're in the winter, it's a very late sunrise, and it kind of goes in this nice steady pattern here. Or how about the height of the tide during a week? Okay, because remember, the tide becomes in, the tide goes out, the tide comes in, and actually, I probably did that backwards. You should think of it like this: the water's higher when it's in, so tide comes in, tide goes out, tide comes in, tide goes out. And there's lots of other examples that you could come up with here. It's really just a matter of justifying what you're doing here. So in this particular case here, notice that for most of these, time ended up being the independent variable here. So not only do you want to be able to look at the scenario and kind of think what it might model here, but you need to be really clear on what these variables would be as well in order for that to make sense. It's a very important skill to have. All right, now here's another question that just deals with interpreting the graph, kind of imposing a scenario on this. Now, we're going to give you a scenario here. So the graph shows the distance of a wakeboarder, that a wakeboarder is from her starting point on a lake. Determine what the wakeboarder could possibly be doing between and at the various points of time here. So just take a quick look at this. Remember, this is distance from point A on the lake, and this is time. Again, we're letting time be along our independent axis. So we've got this up to there, across. Okay, so just now think about that for a second. You could even just pause the video and think about that for a second. We've got a suggestion down here if you're struggling to kind of figure out what this might be. And so here we go. From A to B, since the distance is increasing, the wakeboarder is moving away from her starting point. The change in distance is slow at first and then reaches a constant rate. So what happens here is you might think of it like this: as they move away from shore, they're going relatively slow. But once you hit a point a little ways beyond shore, the rules of boating allow you to go a lot faster. So you hit that point and then you speed up, but you're moving away from the shore. B to C, Now think what's going on here. That's looking fairly constant right there. B to C, what do we got here? Since the distance is not changing, the rider is either stopped or is on a path that keeps her at a constant distance from the starting point. And that's a really neat comparison there. Because when you look at that, immediately you might think, okay, well, they've stopped. Okay, that person has stopped. Maybe they've fallen off and the boat's coming back around to get them or whatever. Or another way of thinking about this, because this is the distance from the starting point, think about it like this. If, let's say, this is the point on the shore, this is point A, at that point right there from B to C, we might be doing this. B to C, kind of moving in a circular arc so that the distance is constant all the way along that particular arc. That's a wonderful alternative way of interpreting that. C to D, the change in direction increases so that the wakeboard is moving away from her starting point at a very quick rate. Okay, so boom, really, really fast. And then what happens D to E? Since the distance is decreasing quickly, the rider is moving toward the starting point at a fast rate. So something's happened here. I don't know, maybe the boat drags her away real quick and then turns around and pulls her back real quick. Now, E to F, the distance again is not changing. So again, either the rider has stopped or again, they're pulling that kind of circular arc there. Okay, but you think about it like this. I mean, the boat pulls her away real fast, pulls her back real fast. Maybe she fell. Maybe she's in the water now. Maybe here they were doing the little arc there, pulls it away quick, pulls her back real fast, and then falls. Okay. Now notice F to G. F to G is coming back. Whoops, sorry, back to the horizontal axis, meaning that the distance away decreases to 0. So FG would be the distance is decreasing to 0. I just said that there. The rider is returning to the starting point at a constant rate. Okay. Now, we keep saying at a constant rate here because we've got straight lines. Now, in reality, that's probably not true, but this is good to just give an idea, give some trends in the data. Normally, you'd expect these lines to be a little bit more curved. Anyway, but it's a good exercise here just to look at that and think about what it's saying. So this next question, we're going to give you the scenario, and we want to go back to the graph here. So take a look. Jeff leaves his home and rides his bike to visit his grandparents. From his house, he bikes directly north for 20 minutes. He then stops for 10 minutes to have a lunch. He keeps heading north for another 30 minutes. And when he hits a bowling alley and decides to play a few games. Okay, well, he's really easily distracted here. This takes him 20 minutes. That's a quick game. He then travels directly home. Wait a second, he plays a few games, 20 minutes? Okay, wow. Then he comes directly home, which takes him 30 minutes. Yeah, never actually gets to grandma's. Okay, whatever. It doesn't matter. That's not the issue here. So we want to assume that he travels at a constant rate, which again is a nice assumption just to simplify the math here, but not very realistic. I want you to think about what that graph would look like, and then I'll show you what we've got here as an interpretation, okay? Just think about that is, okay, he rides away at a constant rate, stops for lunch, rides for a little bit longer, hits the bowling alley, takes him a few minutes, and then he comes directly home. So this is what we've got right here. Now, when you take a look at this, we got to figure out what's going on here because this never actually comes back. So assuming he travels at a constant rate, a possible graph of the distance from home versus time could be. Now, actually, in which case we'd have to finish this up here because this isn't quite correct here. So if we're assuming that this is the distance from home, okay, and this is okay. He rides away, stops for a few minutes, has lunch, rides away, stops for bowling alley, and then he comes home, and it takes him 30 minutes. So he's at 80 here, so 30 minutes would drop him down to there. That's what that would look like. Okay? Now, another way that we could interpret this graph, okay, I could erase this right here, and we could simply go distance traveled, in which case he rides for, 20 minutes, has lunch, rides, and in spite of the fact that he goes home, if we're not concerned with him coming back, if this is only the distance traveled, then this is going to go up as well. Okay? And granted, he's home at this point, but I'm not concerned about his distance from home. I'm just concerned about the distance traveled, like the distance that it reads on his bike, if you will, if he's got a little odometer on there. There's another way that this could work. That line could go up, it could come down. Now, in this particular case here, it does say distance away from home, so it's not the distance traveled. So we'll just say distance from home, in which case this thing drops to zero. Whoops, drops to zero in those last 30 minutes. And that's what we're looking for there. All right, this example right here, we're just going to match a description with a graph here. So let's make sure we can see these. Actually, yeah, you can see everything there. So the total cost of a banquet for a certain number of people, the temperature increase as you heat up water, you get paid $5 for every hour you work, how high a seat on a Ferris wheel is at any given time. Now, okay, number 4 there, let's face it, we just talked about something like that a few minutes ago, and so that should be clear that this is the graph that we're looking at, how high up you go up and you come down. So this has got to be B. All right, now let's take a quick look at this one here. The total cost of a banquet for a certain number of people. Okay, well, now let's think about this. Can you have fractional people? No, don't be mean. Don't be mean. You can't have fractional people, so people are discrete, okay? And so you wouldn't even think about it. Like, you'd have, this would be like 1 person, 2 people right here, 3 people right here. You don't even think about connecting them because that doesn't make any sense. You don't have 1.5 people, but all of a sudden, 2 people. There we go. So right here, this makes the most sense here for the total cost for the people at the banquet, where this would be money, this would be the number of people. Now, temperature as you heat up water, okay, as you heat up water, that sounds like a time thing. Well, temperature is continuous, so is time here. So this would probably be your temp, this would be your time. That certainly feels like it's implying graph D. And you get paid $5 for every hour you work. Now remember, you're getting paid $5. You're not getting paid $5.50, not $5.60 or whatever. You're getting paid in discrete lumps. But the amount of time that you work isn't discrete. Okay, there's these intervals here. So this would be more like a discontinuous graph. So in this case right here, this would be graph A. Okay, takes a little bit of just thinking, again, going back to some of those definitions that we gave you earlier and pulling out that kind of information from the graph. It's not always easy to do. A little bit of practice though, and you'll get this with no difficulty.
At this point, we'll take a look at how graphs can be used to mislead people.
All right, now to finish this lesson, we're going to take just a few moments here and we're going to talk about misleading graphs. Because honestly, math and graphs and whatnot, statistical information, if you will, is used to manipulate people frequently. Okay, and there are some classic ways that sort of thing gets done here. Now, we're just going to really mention this briefly at the end of this lesson. We're really not going to do much with it. To expand this and explore this idea. This is more about just making you aware that this occurs. So it says here, in some cases, interpreting graphs may be difficult, or is made difficult on purpose. Basically to lead people to incorrect conclusions, okay? So for example, take a look at these 2 graphs here. This is a great example of this. Just compare the 2 graphs. Now, this is days of freezing temperatures, 2007, 2008. Now, if you look at this right here, it looks like there's a dramatic increase in the number of freezing days, the days of freezing temps, the number of days we had freezing temps in 2008 than it is to 2007. But that's because the graph here doesn't start at 0. We're starting at basically 80. And so what we've done is we've zoomed in on the top part of the data here. When you take a look at it and compare it to 0, so you're looking at basically the absolute number, the complete value here in terms of the number of days of freezing temperatures compared on both days here. Well, the difference is actually quite minor when you consider the whole value. Right here, we are only just looking at the very top. So we're not getting a sense of what's underneath here. This box here does not represent 84. This box here does not represent 82. It only represents the top chunk of that data there. That's a really common thing to see used whenever someone's trying to give you an opinion as opposed to give you information and allow you to make your own opinion here. Okay, we're just going to take a look at an example of a couple more ideas, and then we're going to leave this. All right, so we're just going to answer the question here about identifying how these graphs are misleading. Okay, let's take a look at this first one right here. Okay, now we're not given any detail about what's on the independent axis or the dependent axis here, but notice again that it's not starting at 0. So we are not looking at really absolute values here in terms of the numbers that are going into this. We're basically just looking at the tops of these graphs. This bar does not represent a number a little bit less than 6, or it doesn't represent 6 even. Okay, this bar does not actually represent a value that's a little bit greater than 5 because it doesn't go down far enough. So the problem is we're dealing with a restricted axis here. Okay, that's a restricted axis. It's not giving us the full detail here. And actually that is basically what's happening over here. Massive increases in house prices this year. Massive increases. From 1998 to 1999, we go from 80,000 to 82,000. That's $2,000. When you compare that to the overall value of 80,000, that's not that big of a jump. But it looks massive because we're not starting at 0. Now, if we were to start at 0 and you could compare that distance to the actual value, okay, and get a real sense of the contrast there, that's quite small. So the same issue for these two graphs here. This one's a little different. This one really gets you if you're not careful with this. What's the problem here? Well, the problem is inconsistent scale. Okay, this is going 1, 2, 4, 8, up to 15. Well, that is not giving us a consistent value here. In fact, if anything, this jump from here to here should be twice as much. From here to here, this is the same distance almost. Okay, yeah, that change in the scale is very, very deceptive, and it is pulling down this data. It looks like this is less dramatic than it actually is. And now here's another one, and this is all about perspective. Okay, as soon as you add this perspective to it here, number of singles sold, well, this looks like 1995 has got so much more than what happened in 90. Like, it looks like things are dropping off really, really badly here. But as soon as you start talking about volume and creating boxes like this, well, first of all, as soon as you start using, in a sense, pictograms here, you have to consider all the dimensions to get a sense of what's going on here. So this box looks dramatically bigger than this one. But is it the volume that's communicating the number that are sold, or is it just the width, or is it just the height? Like, they're all the same width. Is it just the height that's doing that? And additionally, because of the forced perspective here, I mean, this distance here should be technically the same as this distance right here. So is this really all that much smaller? Okay, forcing that perspective creates basically an illusion here as to how much greater this was than this one. Not saying that this one wasn't bigger, but not by nearly so much as it looks like. It's not this distance compared to this distance. It's really this distance compared to this distance. Anyway, hopefully you get a little bit of a sense of how these things can work and how they can be used to deceive you. Just want to encourage you just to be conscientious consumers of data.